So welcome to this session on materials enabling carbon neutrality. Carbon neutrality is very important. It's one of the main targets of EU 2050. How can we achieve at the European level carbon neutrality? So as mentioned also in the previous session about energy efficiency, it's very important to work on the downstream aspect. That means system integration or system development. But in order to have a European value chain fully covered, we also need, when we are speaking about European value chain, that means industry, European research, and that means jobs. So even if we want to have a carbon neutral society, we would also like, for us, for our children, grandchildren, to have jobs and to be able to enjoy this new society, environmentally friendly society. That means that we also have to work on a more downstream part of the value chain, which means materials and components. And so that's why this session is as important as the system session. We have to fulfill at the European level to cover the whole value chain from systems, but down to materials. And of course, we do not have to put all the constraints on the materials. Components, system management have also to take their part of constraints, and we have to use all the new possibilities of new materials in order to work together with the system people. So now the question is, how can the materials help to reduce our carbon footprint? And in some cases, of course, we can say we can just use renewable energies. But usually renewable energies are just producing electricity. But electricity is less than half of the energy we are consuming. So we need other kind of energies. And for some industry, it will be very difficult to avoid carbon. And that means CO2 emissions. So the question is, how can we decrease this carbon footprint? Of course, by increasing renewable energies, but also by developing other technologies, like, for instance, to decarbonize the energy, to decarbonize energy of the feedstocks. And here we think about renewable or decarbonized hydrogen, which may help to consume the CO2 emitted, or CO2 sequestration, CO2 usage, and then also develop some materials to have direct consumption of CO2. And here then we will speak today about also catalysis. And everything has to be done thinking in a way, producing materials, developing materials, but also recycling materials. So from the beginning, it's very important to think about the eco-design from well to wheel and recycling, the whole life cycle analysis. So for this session, we have 4 distinguished speakers. The first speaker will be Professor Schlögl from Fritz Haber Institute of Max Planck Gesellschaft. So Professor Schlögl studied chemistry and completed his PhD on graphite graphite intercalation components at Ludwig-Maximilians University in München, in Germany. And after postdoctoral stays at Cambridge and Basel, he carried out his habilitation under the supervision of a Nobel Prize Professor Oertel at Fritz Haber Institute in Berlin, and then accepted the call for a full professorship of inorganic chemistry at Frankfurt University. In 1994, he was appointed in his current position as director of the Fritz Haber Institute of the Max Planck Society in Berlin. And in 2011, in addition, he was also appointed as founding director of the new Max Planck Institute for Chemical Energy Conversion in Mülheim, an der Ruhr. And he's honorary professor at the Technical University Berlin, Humboldt University Berlin, University Duisburg-Essen, and Ruhr University Bochum. And Professor Schlögl's research focuses primarily on the investigation of heterogeneous catalysts with the aim to combine scientific with technical applicability, as well as on the development of nanochemically optimized materials for energy storage. So with all this background, with all your focus, I think you are really the right person to start and to give us your point of view how materials will enable to reduce our carbon footprint. Please, Professor Schlögl.
Well, good afternoon, everybody. Before I will start my presentation, I want to do a little bit of expectation management here. That's this one. So if you expect me to talk about catalysis and the beauty of physical chemistry, then I disappoint you, because there are so many people who understand this and who will talk about this in detail that I thought, as a first speaker, I should rather much bring this thing a little bit more in perspective. And I should also try to give some ideas of what EU can do in order to actually fulfill this perspective. Because what we recognize is there's an enormous amount of research going on in this area. That is not new. Yeah, but then it's even worse. So I try this, but it doesn't sound very good to me. There's an enormous amount of money in the system, and there is an enormous amount of research going on individual subjects of this, but we are very poor in actually getting this into a technology train and getting this technology train onto the road to commercialization. And now that is always the case in Europe with respect to other parts of the world, as we know very well. But in energy, we lack now the point of time. So even if we are slow, then we cannot afford to stay slow because the energy problem is moving very quickly, and we see this every day, and that is the reason why maybe part of this whole event is here. And when you heard yesterday what Greta Thunberg was saying, then you understand very quickly, if you say in 25 years we have a technology that will help us in 50 years to solve the problem, then we are dead. That's not going to work. And that left me with the idea to think about what can EU do to speed up this whole process. And what I want to bring 3 ideas here. The first one is the dimension of the challenge. Europe consumes every day 10 super tankers full of oil as energy, every day. And you want to replace this. And this is 18% of the problem in the world. So this is enormous. And this is so big that we can never ever afford to do fancy new little things, because by the time they reach the dimension that this is relevant, the whole problem is gone anyway. So we have to rely on robust solutions that are already existing. And we have to think, why are these robust solutions not on the road? Why don't we do this, what should be done? The second reason is we have relied in our energy transformation on renewable electricity that is locally generated. That means, as it was said in the introduction, we generate green electrons and we use the green electrons in the area where we are. Area is plus minus 1,000 kilometers. And then we find, this is maybe useful for 10 or 20% of the energy consumption of a region, but then it's finished because here in Central Europe, where the densely populated area, where there's not sufficient sunshine, simply not enough energy that you can generate. Europe imports 80% of its energy as fossil energy from outside Europe. How can you ever think that we can avoid this? So the core challenge is we have to find a way to have renewable energy as a global commodity that you can trade the same way as we treat now oil and gas from the fossil sources. So the word is simply you have to bring the renewable energy in the tank or in the ship or in the pipeline. How can you do that? You have to convert the electrons into chemical bonds. That's the only possibility that we have. And of course, many people think liquid hydrogen is a good solution. Personally, I do not think that this is a good solution because you have to make hydrogen that is clear, but chemists are, I think, more clever to make better forms of usable hydrogen than hydrogen itself. So there are all these transport vectors. I don't have to allude to that. You know this very well. The interesting question is, we all understand this, and every component of this technology is existing, and yet we have never compiled it together. We have not been able to show to the world that that's going to work. Japan has started doing this about 10 years ago. And I just visited the place in Australia last week where they do this. And okay, that's fine, that is small, but at least it is working. But in Europe, nothing is working. Why? Because we have decided that we would like to do a transition that is essentially focusing on electrons only. And we have forgotten that the material part is at least half of the solution. As you said, half of the solution. So what do we have to do in order to change this? We have to think about the many interfaces between politics and science and different disciplines in science. They all develop isolated solutions, but they do not respond to the system challenge. This is a systemic challenge, and so the research on it has to be also systemic. And that's not the case. This is very simple today. We have lots of there are catalysis people, there are engineering people, there are electrical people, there are people who make strange laws, or regulatory conditions where they say CCU is not existing, that is not an energy solution. Yeah, why is this? Interesting question. And all that hampers us of creating a market. And as long as we don't have a market for these kind of materials, then we will never make it technologically, because you need a driver for that. And science has produced lots of solutions already. So it's not that the fundamental science hasn't done anything, and the next speakers will allude to that, what we know already. But nothing of this thing has ever come to the market. And as it is not in a marketplace, it's not on the road, it will not contribute to the energy challenge. My suggestion thus is that we need to look again how we spend our research money and how we organize research in Europe. Because the point is simply there are too many interfaces. What we need is large projects, or at the best one large project that solves the problem of materials in energy. And this has to have a superstructure that looks into two dimensions. The one is it has to speak to policymakers. Many policymakers simply are not aware. You all know what we discuss. But when you talk to policymakers, they are not aware of that, because there is not a very good contact between science and politics. And the same is true to the general public. So how many people in the general public know about the options of CCU? And how many people know about synthetic fuels and their operability? They do not. Simply because we as scientists do not feel the necessity to do that. But of course, if we don't do it, who else should do it? We have to convey this message. And such a superstructure has to be organized like an industrial holding. So there's a superstructure, the core of it, that does all this politics and the management. And then we have to have clusters of scientific activities directed into the different, disciplines. So we need science, of course. Science is the basis of everything, and we still need science. Also, I have said we have already done something, but we need a large fraction of engineering and scale-up. And that is at the moment probably the biggest mistake in the EU organized research, that this transition between science and engineering or science and scale-up is very weak. And it has to be much stronger. We also need to think then about demonstration plants, and demonstration plants are not things that are sitting in a container, but demonstration plants are world-scale demonstration plants. That requires a significant amount of private money, and that requires also a significant amount of fintech, because you need to find the investment for that. It is not on the EU to finance these kind of plants. Private investors have to do that. But private investors will only do it if there is a clear path to success. And the important fraction that is missing for the clear path of success are the regulatory boundary conditions. At the moment, they are adverse to this kind of chemical energy carriers, and they tend to change every couple of years. And both things are absolutely detrimental, because you need stable conditions for decades, and they need to be technology open, that everybody who has a good idea can continue there. And largely and lastly, we also need science in law and in social sciences, because there is a strong interaction between our society and the technological options. And as long as we ignore this and think energy conversion is just a problem of chemistry or physics, then we are doomed to fail. That will not work. You can see this very quickly when you think about E10, or when you think about biodiesel and all these things. They fail because it was done without asking the public or integrating the public into the development of this technology. People are simply not prepared just to accept a solution. They want to be part of the decision making. And that thing is largely ignored. Now, what I suggest is really to bring this together in one big project. And as I said, this has to be hierarchically organized, and you have to have a superstructure that does it. And any of these clusters, of course, has many individual projects. That's all fine, as we do this usually. But what we have to do new is to remove all these boundaries between different projects. And that is something that is not so difficult to do. It is just something that we have to understand, that the research on energy has to mimic the complexity of the problem that we want to solve. Of course, such a project is way more complicated than a normal EU project, that I am very well aware of. But the challenge that we want to solve is also way more complicated than just solving a catalyst improvement. And so we have to match this. The new structure that I would propose should really be in a position that it mimics or it mirrors the complexity of the problem that we have. Now, how far are we? Is this out of the blue? No, it's not. You will probably have heard, or you might see, Energy X was an activity that was trying to draft such a proposal structure. This has happened earlier this year, and the day after tomorrow, the result, the white paper, will be presented to the EU Commission. So I hope that this has some impact. And I would like to end my presentation with the idea you should not think about why this is difficult to do research that way. You should think about we have to have a bold solution, because if we don't have a bold solution, we will not match this enormous challenge that we have ahead of us. It has to be much bigger and much better than what we did so far. And in order to do that, my suggestion is to bring the complexity to the research and not to exclude the complexity from the research, because then we probably will always stumble across these many interfaces that we see in the present. So far from my side, I'm sorry that I haven't talked about iridium oxide and copper and nickel and all these beautiful things, and I would have loved to do that, but I thought it is more important that we find a direction, what we have to do, rather than to go into individual details. I'm very confident that the follow-up speakers that will come will go into some details of these things, and that is the reason why I leave you with my general ideas. Thanks so much.
Thank you very much. Thank you. Thank you very much, Professor Schlögl. So I propose that we have all the speakers giving their presentation, their talks, and then write down the questions, and there will be a specific session just for discussion and questions for the sake of time. So after this very nice introduction, I would like to introduce our second speaker, Professor Gabriele Senti. Gabriele Senti is full professor of industrial chemistry at University of Messina in Italy, and he's also the president of the European Research Institute of Catalysts, ERIC. And the research interests are in the areas of applied heterogeneous catalysis, sustainable energy and chemical processes, biomass conversion, and environment protection. So Professor Senti, he was coordinator of the European Network of Excellent IDCAT, and he's the current president of also the International Association of Catalyst Societies and vice president of the Inter-University Consortium of Science and Technology of Materials. And he was coordinating more than 20 European projects, besides many others, also national industrial projects. So he has received several awards, involved also in various editorial activities, and that Professor Schlögl was saying we have also to communicate, advertise. So papers is one way, but more among scientists. And so he's a co-editor-in-chief of the Journal of Energy Chemistry. And he was also chairperson of many international conferences. So Professor Senti, please.
Thank you, and good afternoon to all of you. I decided to have a few words very complementary to what was presented from Robert. We agree on this. And I was trying also to highlight some of the points, so because sometimes when it's short time, it's good to fix. The first point is that I think we need to remember one thing. Often is asked what will be the cost for Europe to go in this direction, to go to carbon neutrality. I will say this is not a problem. The problem is what is the cost if we are not going to this direction. And just to give you an indication, there are some interesting recent papers that estimate what is the cost for Europe in terms of cost for climate associated to climate change per tons of carbon dioxide, and the estimation average is 400 euros. So this is the cost that we have to face if we are not going to this direction. So an investment in this direction is very worth. And also the other point is that the real limit to go in this direction is not more economic, but is technological. So we need to invest on technology to really achieve and to transport this to reality. Well, of the various aspects, I was focusing just only on one aspect because time is short, which is carbon dioxide use. We have two possibilities. One is to produce, as was mentioned, Robert, in terms of solar fuel, so to go to chemical energy storage. This is a very important component, and we have just not only to because we have fluctuation in the use of renewable energy, but also because we need to enable a kind of economy on world scale of renewable energy. So we need to transport from long distance renewable energy. So we need to have a way to store in chemical way this. But the second is that we need also to create a carbon circular economy, because this is equally very important and integrate very well with this part. And if we go now to more specific to the kind of carbon dioxide technology, the point is that today we still need mostly to produce hydrogen by electrolysis, for example, and then use hydrogen by catalytic conversion of carbon dioxide. And if we are looking to this aspect, we see that we have a penalty in terms of energy because this is something like, we lost something like 30% of the energy that we are putting in the system due to this conversion. So what we need is to try to bypass and to go to next step, of course, of material and technology to go in this direction. And we have essentially two main possibilities to go in this direction. One is to use a proton and electron rather than hydrogen itself. And so in this way, we need to develop a kind of photoelectrocatalysis system and technology related to this. But we have a really technological gap today to go in this direction because we don't have still robust and productive and selective material to go to this. So the problem is really to develop the material and integrate with the technology and the cell to go in this direction. And so we need really to integrate these between material development and development of industrially scalable type of cell, flow type of cell. And in this sense, we are going progress in general terms of artificial photosynthesis device and related material, but to go to this, we need really to control much better the complex machinery, which is from nano to macro scale. And this is really the point. If we are not able to integrate this different level, and if we are making this a separate step, also was mentioned from Robert before, we are just too slow process to go. We need to integrate and to make really a different way in which we are thinking and making together the development in this area. The second possibility is to couple the oxidation part, because always we have an oxidation. For example, it can be oxidation of water, but which form oxygen as a side product. This is the limiting steps, and also most of the time we are not able to use the oxygen which is produced. So we are losing part of the energy going in this direction. And this is the reason why we need to design a new approach in which we can have alternative oxidation, and we have a great opportunity to go this, to use some of the product which form, for example, bioethanol, just to give an example from biorefining. So this is giving us the real opportunity to have integration between solar and biorefinery, and of course to go in the direction to use alternative carbon sources in a much more efficient way. But for this, we need to develop a new concept in terms of cell, in terms of materials, in terms of integration with other elements like photovoltaic cells. So we have a lot of work and activity in this material to go, which is the real enable material and technology to make steps in this direction. I just mentioned carbon dioxide, but just to say that we have a huge area in this. We need to make a better system for water, for nitrogen, and so on. So this was just an example, but we can translate this to many other areas. And was mentioned also from Robert that we needed to identify much better what is the technological and material sequence that we have to go. We are now mostly on thermal catalysis in this area. We need to make the next steps to electrochemical, then photoelectrochemical and photocatalytic. So we need to design, but this don't mean, yes, very shortly. This don't mean that we need to leave photo at the end, because we need to produce all the knowledge in this direction. And we have also other possibilities, just to mention, for example, the use of plasma, which is very interesting. So essentially, just to conclude, we need to have new approach. It's not just an extension of the concept that we have today, for example, for catalysis, but we need to really develop completely new concept in terms of catalysis to make, because it's not just an extension, but new area. So we need to develop conceptually new catalysis. And to go to make this, we need really to join the fundamental and technological development, so to have a wider level and also a long-term approach, as mentioned, to have some project going which combine a fundamental to applied and engineering aspect. Okay. Thank you very much.
So, as you can notice, this for the second speech, one I noticed very important point, how can you bring research to innovation? That's for materials and from the system. So as mentioned here by Professor Santi, first to use CO2, there can also be some direct conversion, but there is another way, more classical way, more robust solution, using Professor Schlegel's words, which is using decarbonized hydrogen. And this will be, I would say, more or less the topic of our third speaker this afternoon, so Mrs. Anne-Chloé Devic. And after her studies of chemical engineer and Master of Science in Polymer Chemistry in Montpellier, in France, Anne-Chloé Devic occupied various positions in research innovation, mainly scale-up project management in the UK, in France, in Belgium, for ICI, and then Huntsman. She joined the technology department in Repsol SA in Spain in 2002 as senior technical advisor in materials innovation. And after 3 years of a mission spent in CEFIC in Brussels as research and innovation manager in the materials topic, she returned to Repsol Technology and Corporate Venturing Department as plastics circularity manager. So Mrs. Devic, please.
Okay, thank you. So I think we'll complement quite well the presentation of Gabriele Santi. I will give a concrete example, actually, of a project that we have on a photoelectrocatalyzer. So I will just put a bit of context on the hydrogen production and how we use it and how we need it in Repsol. So this is it. So the context, the demand of hydrogen is about 55 million tons per year, 63% actually applied in chemicals and 30% in refining. Knowing that Repsol is a refiner as well as a petrochemical producer. And the main technologies are steam methane reforming, coal gasification, and then you have the electrolytic hydrogen, which is the lowest percentage, but which has the best potential for decarbonization, depending on the energy mix, of course, of the type of electricity you use. The main applications for the low carbon hydrogen, as we say it, is the electrolysis coupled with renewable electricity, which is the most at the moment used by companies, or where you can find many projects starting to be developed. But then you have also the photoelectrocatalysis. And this is an emergent technology that does not require external electricity input, and the water splitting is achieved with the sunlight into a PC unit. And it is believed that by 2030, up to 250 to 300 terawatts of renewable energy excess could be converted into hydrogen for its use in many, many sectors. The use, I will not spend time on this for mobility. It's clear that also hydrogen will be an important vector. So in Repsol, we need it in refining for desulfurization and hydrocracking. We are expecting our hydrogen demand to increase significantly due to higher fuel quality requirements, and also increased consumption of hydrogenation for vegetable oils for advanced biofuels, which will still be needed in the next 50 years, for sure. All these green hydrogen sources will enable refineries and chemical plants to reduce their carbon footprint. The hydrogen production accounts for around 20% of our direct CO2 emissions, as for information. Now, the most important, so as running a group on materials research and innovation, and that's why we are here for today. We have been developing this project since 2015, more or less, and it's a proprietary photoelectrocatalysis technology, and it's a joint co-development between Repsol and Enagas. And we use solar energy, as I said before, without the need of electric source. And the very positive aspect is the OPEX is very low due to the solar energy input. Of course, we are based in Spain, so that's a big advantage. And it's independent from natural gas and electricity costs. CapEx, yes, it is intensive, and this is the whole point of the development at the moment. So we have an integrated and modular process, but then the problems are efficiency and stability. So we are working in developing, in improving those efficiency and stability. We have 2 patents, if you are interested to look at this. The prototype is being built at the moment on site at south of Madrid in Móstoles. So we are at TRL 4.5, and we expect to be to TRL 6.7 in not a very long term. And the reduction potential for the carbon footprint against the conventional process, the steam methane reforming, is 90%. So this is a very concrete example that I wanted to present. Thank you.
Okay, thank you very much. Thank you very much. So here you have seen us. Usually, yes, when we are speaking about hydrogen production, everything thinks about electrolysis, water electrolysis. So it's good that you also pointed there is another way to produce hydrogen using solar, not only PV electrolysis, but also this photocatalysis way of production. And even we can also use solar heat, also then coupled with a high temperature vapor electrolysis, where we could also then, that's another way, very interesting way, with a very high efficiency to produce also low carbon hydrogen. And that's why I was just using that. But this is something we may also discuss afterwards. You were sometimes speaking about green hydrogen. Personally, I prefer to speak about low carbon hydrogen, because the target is to reduce CO2. So we have to think about CO2 and not about only renewable. There are other sources of very low carbon electricity, which also then may be used for chemical processes or hydrogen production. So now we move to our last speaker for this session, and then it will be interesting to have a point of view of a second very big oil producer worldwide, which is Total. And then I will present Mr. Chaperon. He's the Vice President of European Public Affairs at Total. And Mr. Chaperon graduated in marine engineering from ENSTA, a French leading engineering school. He joined Total in 1980 as geophysicist in the exploration division before being appointed to head Total's gas business in Japan. Then he moved to Taiwan, to Qatar, so a very nice international experience. And in 2011, he managed the acquisition of SunPower, now one of the leading world solar company in which Total holds a majority interest. In biomass and biotech, he also negotiated and developed a partnership with Amiris, a global biotech leader, opening up new and promising opportunities in advanced biomolecules for Total. And in September 2016, he was appointed Vice President of European Affairs for Total Group based in Brussels. So Mr. Chaperon has a very big and extensive experience in the field of energies, and so it's very interesting to have also your point of view.
Thank you. Yes, I am a lobbyist. So, you know, it's a challenge for me to address science community, even if my background, as you mentioned, has some long science behind. So when I started to prepare this paper, you know, I was convinced that the material science is a disruptor and that we need a disruptor in this field to achieve carbon neutrality. So this was something which for me is really, I was convinced. What was my discovery by, you know, going into all what Total is doing in research and development? because I had to look at this within Total to see all what we are doing in the various part of the group. What I discovered is it's already on the move. So that was a good news that I share with you. It's not a dream, it's already on the move. So that's the good parts, and I will try to convince you. So it's not all about data, if you want. It's also about material science for the future. On the 5 pillars of our research and development program, in which every year we invest €1 billion, all of them, we have material science as a challenge. In all of them. There is not, all across. So what I'm going not to do today is to go across the board, because I will need probably 2 hours or 3. So in 7 minutes, I will focus myself on batteries, a little bit on CCUS. I don't think I will have time to go in bio, in all the biochemicals and all what we are doing in bio. And I will try also to look at the game changers that we can find in the battlefield. So let's start with the batteries. So you may not know, but Total is Saft. Saft is the biggest European battery manufacturer, but it's very small compared to the Chinese or Koreans. But at least it's European. So we have a big project of going from traditional lithium-ion to solid-state battery, which is a game changer for the future. So the solid-state ion is to have basically an electrolyte which is in a solid state, kind of specialized polymer, if you want, with improved positive electrode and improved negative electrode. The target in terms of performance is to go from today 275 watt-hour per kilo or 700 watt-hour per liter to go to 430, so really step change the density, the energy density, and 1100 in terms of watt-hour per liter. I remind you that the Tesla, the battery is roughly 800 kilo, go to up to 900 for 80 kilowatt type of battery. So the density, energy density, is a key challenge. We have also another one challenge is security, safety, if you want. And by having a solid electrolyte, you really improve the safety of your battery, which is important. Longer life is important due to the electrochemical stability of solid electrolyte. And we have less use of critical raw materials such as cobalt. And of course, the purpose of that is to trim costs down. Trim costs down. So the key to success is material science, honestly. It's solid electrolyte material with ionic conductivity equal or better to liquid electrolyte. This is a challenge. A solid electrolyte membrane, mechanically able to prevent lithium dendrite or dendrite, I don't know in English, from causing short circuit and then explosion. It's active materials electrochemically stable with the chosen electrolyte, and it's high-speed manufacturing processes, creating solid matrix structure, very different from wet sponge structure of the current lithium-ion technologies. So this is a project up to 2025. So we'll start the world-scale developer or demonstrator soon, in order to be able to have by 2025 the technology in place for scaling up for the models of the car industry in the second part of the decade. So this is important. It's a material challenge. So the battery, I'm not calling it revolution. It's an evolution of the batteries, but it's important for the car industry, and not only for the car industry, for storage with all the renewable intermittencies to find. So my second is CCUS. So it has been already covered, so I will try to cover in a different way. So if we want to solve, looking at the world issue on CCS, basically we have to keep in mind that we have to capture and store 3 billion tons of CO2 per year, per annum, which means something like 600 projects of 5 million tons each per year, which is an investment, roughly speaking, of $150 billion per year. If you look at Europe, you divide by 10. You just divide the figures by 10. 300 million tons per annum of CO2 to be stored. 15 billion to be invested. The challenge is 60% of the CCS cost is capture. And in capturing, 60% basically is materials. Challenge. So the main challenge of CCS is materials. Of course, it's also acceptability. Yeah? That's fine. So it's either under the sea, that's onshore. That's another story. So we need, material science. So what we are doing within Total on CO2 capture, we select and optimize right materials. We are coupling multi-scale from nanometer to micrometer, exactly what you said. Characterization by advanced analytics with high-speed computing, treatment, and simulation. I just remind that Total has a 31.7 petaflop computer, high-speed computer in Po, so it's of course used also for material science. For the CO2 use, we have put in place strong partnership to develop complex catalysts. We have done some in operando, which is observation under real conditions of process, test to monitor catalyst evolution during reaction. As we try to have is using cyclotron, which is unfortunately expensive, but can give characterization at phantom second type of appreciation, which is, well, something in which we can try to improve fast. So no time for the bio. So if you want to ask me a question, I will answer the question on the biochemicals. So let me look at the game changers, because it's not only on each of these business line, it's also the tools that we are using. The tools, if I look at the list I have and that we use, is of course try to improve the modelization, having a molecular or atomic type of modeling, using this very high-speed computing type of process. In operando characterization, I mentioned, is also very important in the catalyst development, in all what we are trying to do using catalysts in this material science type. Manufacturing 3D, we didn't mention, but it's also a game changer. It exists today. So we are in a scale of printing race down to the potential scale of molecular atom scale type of printing. And this is going to be a game changer for solar industry and eventually for batteries, where we have to have these capabilities to improve the process in the industrial process using this technique. I was surprised myself looking at Total was using already these techniques to design some specific piece with specific materials to go down in the deep offshore, more than 1,500 meters, using this printing machine technology already. It's not in 20 years, it's now. The last point is, just on time, high throughput screening, where we develop all these technologies, the tools already in practice everywhere. But the challenge that we have is also to address this high throughput screening in higher temperature and in clean fab chambers, which we are trying to develop in order to advance a little faster in material science. No time for biolab. If you want also to address a question on solar, I'm ready. It's also my background, solar, so I can tell you a nice story about material for solar business. Thank you.
Thank you very much. So I would like now to ask to the four speakers to come here at the stage and to start the discussion. We have about 10 minutes for questions, discussions. And so please, I would just ask to the people to present themselves shortly, name and affiliation, and then also quite short and detailed question. Please, Mr.
Good afternoon. My name is Laurent Zibel. I work for Industry All European Trade Union, so the European Federation of Trade Unions in Manufacturing. I would like to introduce a completely different perspective on materials for carbon neutrality. That is the perspective of circular economy, because there is an enormous amount of energy and carbon which is embedded in materials. And I believe that the purpose of circular economy is the eternal use of materials. Like aluminium already performs that. The point is we need to extend this to all other materials in order to maintain the purity of these flows. And in order to do that, you need, of course, sorting technologies, right? But you probably also need to limit the number of materials to be used in order for these material flows to be manageable. And the question is, and I'm specifically talking about alloys or plastics. And is there anything planned in terms of research and innovation regarding what would be the optimal mix of materials to enable this eternal reuse of materials over time?
So we are already doing it. Huh? So chemical processing for recycling plastics already exists. Of course, we have to improve the process. The problem today is not the technology that we are using, is the material coming inside, which means we do not have enough. Our industry do not have enough material to be recycled to manage the system. So I'm not saying that because of course we have to improve the chemical process. So it's a catalyst. It's mainly sorting, as you say, les intrants, entrants. It's also having a better catalyst into the processing. So we have to improve, but we do not have a lot of incentive as an industry to do it right now because we do not have enough to process. So it's the whole value chain has to progress together. So that's my part of the answer. Maybe you have another one.
Yes, the waste, well, we have the objective of taking off waste from the landfill. And rightly said, it's not that easy to have local sourcing of waste and different types of waste also. Now, on the materials application side, there is a lot of work to do also. Design of new materials so that it's better recyclable, that it can be reused. I mean, on the research and innovation agenda, it's seen without any end the list of different research lines that we have to tackle in that circular economy challenge.
I want to address one specific problem that you mentioned, and this is sorting the material, because recycling doesn't make much sense if the recycled material has worse properties than before, and that comes from impurities. So I think managing the impurities is a critical issue. In hydrocarbons, that might be go away with other solutions, but in metals or alloys, that's a very big problem. I only remind you about steel. When you buy steel from IKEA, then you see, so rust-free steel is not rust-free because there's a trace of copper inside, and that gets these brown points on the steel that you get. That is an issue because it comes from cars. So these kind of problems to solve is a very big problem that we have to do. There are research programs alongside, but I think people have not paid enough attention to the quality of the recycled material.
Thank you. So we now move another question.
Thank you very much, and thank you for the excellent presentations. I mean, there was a fantastic, how can I say, disruptive dissemination of knowledge. So, Professor Schlegel, my name is Eden Mahmoud. I am a professor at the university in Constanța, Romania, but we are part of the EIT raw materials. And my question is that the structure that you mentioned, this MECA corporation that has to be at the EU level, why should be different than an EIT KIC, the Knowledge Innovation Community? What is the difference what is the weakness of the EIT model that you consider?
As long as it comes to science, there's no difference, so that's all fine. But what I think is not well enough covered in your model is really this transition to market. The last part of the whole story is if there is no feedback between market and economic people back to science, then this is not working because there is no linear chain in evolution. This has to be done in a recycled way, and that is largely still missing because the communities between economics and market drivers and policymakers and scientists, they are completely disjunct from each other. It's very difficult to get them to work together. That is the innovation part.
Good afternoon. My name is Desio Miranda Barbosa. I work for University in Norway. My question is, do you see any real possibility to create a synergy between hydrogen use and CCS?
Oh, I'm sorry. Yes, the answer is yes. This is the whole question between the green hydrogen or the blue hydrogen. So blue hydrogen is using methane, so natural gas, if you want, and then you do reforming of this natural gas, which give you hydrogen and CO2. But you have the CO2 at high concentration, and of course you capture and store CCS, this CO2, and then you have so-called blue hydrogen that you reinject in the economy, which is zero carbon, so type. Between the, of course, green hydrogen, which is using different type of technology from renewables in order to manufacture green hydrogen. So if you want, you can use electrolyzer using solar or wind or different green technology. So, of course, there are synergies between CCS and hydrogen. So now it's another story, as I mentioned, storing the CO2 somewhere in the nature.
And then just to complement for hydrogen, there is a cost also difference today. Of course, producing hydrogen from SMR as today is the cheapest way and the most used industrially. But the cost of producing decarbonized, low-carbon hydrogen is decreasing very sharply in the last years. And today, when you want to compare blue hydrogen to low-carbon hydrogen, green or purple or whatever, but from low-carbon electricity, we have to take into account CCS cost. Yes. And here you see the balance between the two-way blue and green hydrogen becomes smaller and smaller. And that means then, as mentioned by Professor Schlögl, the market has to be there. And the market to be there, we need policy.
Yes, and also it's a race, exactly as you mentioned, which is good, in a healthy race, between decreasing the cost of the CCS and on the other side, decreasing the cost of the green hydrogen, if you want. So there is a race there. So today the cost of CCS is roughly from 100 to 250 euro per ton of CO2 abated, stored, if you want, roughly speaking. And as I mentioned, 60% is the capture. So now if you look at the US, in US, the plan that they have in terms of cost is reducing the capture cost to $50. So if you have $50, which means that your overall cost of CCS is abated to something like, say, 80 euro per ton or dollar per ton, I don't mind, you know, then the hydrogen green needs to be very cheap to compete. So anyway, you need both. So the question is not, you know, because both will be developed.
Yes, it's complementary. Maybe just a last question, a very short one before closing.
Thank you. Philippe Jacques from the Energy Materials Industrial Research Initiative. I had a question for Mr. Chaperon. I would like to hear your point of view about the lessons you can share with us regarding the failure about the photovoltaics industry in Europe in the past, and how we can avoid this regarding batteries, for example.
I know the answer. It's Chatham House here. So I'm going to tell you the story because I know the story, of course, from day one on the solar photovoltaic. In Paris agreement, I was participating to the number of world tops best Fraunhofer Institute for Solar in the world make a big announcement, 30, 30, 30. So which means 30 cents, 30% efficiency, 2030. Today, we are at below 25, so we are below the 30. We are not at the 30% efficiency. Chinese are 18 to 20, SunPower is 25, but still it's not 30%. So we still have progress. So this is on the performance side. The story on PV was the combination of massive investment in Germany, subsidizing demand through the feed-in tariff at a high level, costing Germany a hell of money. And on the other side, massive subsidy from China on the offer side, not on demand, but on the offer, subsidizing their industry massively. With these two huge impact, we are talking about not billions, but tens of billions of euro into the system. We are today at grid parity. So this is so. Now there has been an agreement, secret, between the top German and top China, whereby German has privileged to have their car industry and chemical industry in China against their, let's say, solar industry or the European solar industry. It has been a kind of deliberate will behind. So this is a story. So I'm sorry to say, but this is what's happened exactly. So I'm not judging. I'm not saying it's good, it's bad. At least for climate, it's good. Because today we are at grid parity, and we can probably anticipate that the solar PV will be the cheapest way of producing electricity very soon, at least where there is sun. So you can massively scale this technology. The problem is more the intermittency afterwards to manage. Switching to your second part of the question, the batteries, it's an excellent question. I just comment what my CEO said regarding massively investing in battery, because it's a question addressed to us, because we are SAFT, so it's a question addressed to us. We put three conditions. Conditions number one is it has to be a team, not one company. So it's a team. It has to be a few countries, a few companies sharing the risk. And not only the battery manufacturer, but also the car industry, because if one is doing this, it's also for customers, which are the car industry. So the system, the ecosystem between the battery manufacturer and the car industry should. The second condition is you need to be let's say at par with the Chinese or with the Koreans or with US in terms of subsidies. They are massively subsidized. You need to be, level scale. And the third one is to be sure that in coming years, if there is an attack which is massive dumping from, let's say, China, you are not going to be killed next day by this, and that Europe will defend its industry, which what Europe has not done for solar. They have to do it for batteries. So it's a kind of answer to your question.
Thank you.
Chatham House.
Yeah. So thank you. So we are arriving at, we are running out of time. We have only 2 minutes left. So first I would like to thank all the speakers. And I think as a summary what we can say is using materials for carbon neutrality, there are some scientific, some technological solutions on the way. But as mentioned from the different speakers, what is important is first to bring research to innovation. That means to bring from labs to industry, and also to have a market. And that means not only to work on technology, but also work on policy. And Professor Schögl said it at the beginning, we also have to work on how to advertise and to communicate. And this was just also mentioned by Jean-Éric Paquet at the beginning. It's very important for us to let the society, to let the politicians know what we are doing and how we can be helpful to European society. And as also another, from my point of view, is we have to bring renewable energies as a commodity. And that's also very important. And in order to help this to become a commodity, to become also industrial, there are in the European level some strategic value chains. I come back to the value chains. It is also running for batteries, for microelectronics, for hydrogen. We're discussing all that. This is one part for industrialization, and whereas in Europe, working on materials, working on different technologies like batteries, like also hydrogen technologies at the materials, at the component level, can be a good link to develop components, to develop materials, to validate some systems, that's research, and then to go to the strategic value chain with the IPCIs in the discussion today in order to deploy and to industrialize all these solutions. And here we see a really good connection between Horizon Europe, research, and what we are looking at the European level with DG GROW, with GD competition, which is to have a very strong European industry. And so that's, on these topics, I think a very nice complementary, and normally, I hope so, with Horizon Europe, we will be able to bring solutions to the industry, but we also need all the help and the contribution of the policymakers to make stable policies, stable regulations, and to help new technologies with incentives to be competitive from now to old and historical technologies. So with that, I would like to thank you all for this session, for contribution, and all the speakers. I think we can applaud them again. Thank you very much.